This is our calculus lesson 3, continuity. So first of all, let's talk about the definition of continuity. So a function f is said to be continuous at x equals to c if and only if, the first one, the limit must exist. We're going to express this in our limit notation, x approaching to c f of x exists. What can we derive from this? I've talked about this in my last video. A limit exists only when its right limit equals to its left limit. So we can say limit x approaching to c minus f of x. This equals to when limit x approaching to c plus f of x. Our second rule is f of c is defined. What does that mean? That means at x to c, f of c is a closed dot. It's not an open dot because that would be a hole. Since the f of c is defined and limit must exist, here comes our third rule. The limit must equals to the actual value. So the limit equals to f of c. These are the three rules they have to memorize, or on the other hand, you have to fully understand to testify if the function is continuous. Let you do some sketching. The first one is f of c is not defined. When a function is undefined, we know that there's a hole, right? So that x equals to c, f of c, we have to put an open dot over here. What about when limit x is approaching to c, f of x does not exist? We know that when a limit does not exist, when its left limit does not equal to its right limit. So we can say there's the asymptote at x equals to c. The function may look like this. Because its left limit is going all the way to infinity, but its right limit is going all the way to negative infinity. So the limit does not exist. What about this? F of c is defined and limit exists, but they're just not equal. Which means that f of c is defined elsewhere. We can say there's a hole over here. The limit exists because the left limit equals to its right limit. But at this point, f of c is not defined, which means that it's defined elsewhere, but at the same point of x equals to c. We can say there's a point beneath it or like above it, doesn't matter. This is c, this is f of c. I mean, it is defined at x equals to c, and it is also the limit exists, but they're just not equal because they're corresponding to different y values. What about f is continuous at x equals to c? That basically means this is the most classic way. Put it like a closed dot over here, this is c, and f of x equals c. There's also another type of discontinuity called crazy oscillation. One famous example will be y equals to cosine 1 divided by x. Let me show you what it looks like on decimals. This is the y equals to cosine equal 1 over x. This is discontinuous because it's always oscillating. The right limit, the left limit, they're always changing. They're not equal to each other. That's why it's discontinuous. But it's not important in our topic, so we can skip it. If a function f is not continuous at x is equals to c, the discontinuity may be one of the type 3s. We have point discontinuity, which we talked about before. There's a hole at c, f of c. A jump discontinuity means that there's a change of value. For example, the value is over here, but at this point, it could also be equal to another value. This is called a jump discontinuity. This is a jump of the values. An asymptotic discontinuity, it basically means that there's an asymptote which causes For example, let's just say x equals c, calls the function the left limit unequal to the right limit. Let's move on. A point discontinuity is said to be a removable discontinuity because the function can be redefined at the point in such a way to make the function continuous elsewhere, right? So we could just make a conclusion that only point discontinuity is continuous. I mean, it's removable because it can be redefined elsewhere. Whereas jump discontinuity and asymptotic discontinuity, they're non-removable because they cannot be redefined elsewhere. There's also another method to tell if the function is continuous, but this is only for a closed interval that we don't denote it as this equation. What it basically means is that for our regular limit, let's say we have a function, we use left limit approaching to a certain point and right limit approaching to a certain point to define if this function is continuous at this specific point, right? And for this, it's kind of the other way around. Since there's a closed interval, let's just say this is A, let's say B, we can't testify the limit using right and left because it's not going from infinity nor negative infinity. So it's kind of the other way around. When we're trying to testify if this one's continuous, so from the left end, we use right limit. When we're trying to testify if the right end is continuous, we use left limit. This is kind of, it's kind of like the other way around. If it's smooth here, if it's also smooth here, that means the whole function at this closed interval is continuous. This is one example. This is a graph of a half circle with a radius of x equals to 5, right? And it looks like something kind of like a half circle. This is 0, this is, the value is 0, but the x value is negative 5, this is 5. So from the left end, we use right infinity going from here, and from the right end, we use left infinity going from here. Since it's smooth and also smooth, so it's just continuous. Let's move on. Let's do more sketching. We have to find the values in which the function is discontinuous. We also have to identify which discontinuity this is. Also identify if it's removable or non-removable. Keep in mind that only point discontinuity or whole discontinuity is removable. Let's look at the first one. We can simplify the whole equation as f of x equals to x minus 3 times x plus 3 divided by x minus 3. There's a whole at x equals to 3. So we can say a value at x equals to 3 is undefined. Since the whole can be removed, and the whole function can be simplified as f of x equals to x plus 2. And if you plug x equals to 3 in, you can get 5. This is defined. Since it can be redefined elsewhere, this is a point discontinuity. Since it's a point discontinuity, this is removable. The function will look like, so x plus 2, this is 2, but it's undefined at x equals to 3, f of x equals to 5. We have to put a closed dot over here. This is what it looks like. What about b? So first of all, the function is undefined at x equals to 3, right? And we could easily tell at x is 3, there's a vertical asymptote because it's an inverse function that looks like this. You should be very familiar with this type of function at x equals to 3. Since there's an asymptote, we can say this is an asymptotic discontinuity. Since it's asymptotic discontinuity, it is non-removable. Ooh, there's a little typo. Non-removable. Because the left limit doesn't go to the right limit. Is it going elsewhere? What about this one? Is it continuous? The answer is yes, it is continuous. Because it has its own domain, which is x larger or equals to 1. From this specific domain is always continuous. So it is continuous. This is always defined. So the third thing will not be applicable. What about the fourth one? When you see a piecewise function, the first thing that you need to do is to test left limit and right limit. So the left limit will be limit x approaching to 1 minus. Since it's smaller than 1, we have to use a function of x plus 2. This will give us a value of 3. And the right limit will be x approaching to 1 plus. Since it's larger than 1, we have to use 2 minus x. So this is equal to 1. Since these two are not equal, we can say it is discontinuous. And it is a jump discontinuity. So the first thing is at x equals to 1, there is a discontinuity. And 2, this is a jump discontinuity. Third, since this is a jump discontinuity, it is non-removable. So what does the function look like? There's a breakpoint at x equals to 1. And from the left side, when x is smaller than 1, we have to use a function of x plus 2. At this point, you have to be very careful that there is no equal sign. So no matter where at the breakpoint, we have to put an open dot. There's a y value of 3, and this function of x plus 2, so it roughly looks like this. And when x is larger than 1, the function is 2 minus x, and with a value of y equals to 1. So here's a open dot at y equals to 1. The function is 2 minus x, so I'll say roughly looks like this. This is it. We have to find k so that f will be continuous at x equals to 2. What does that mean? Like what I said before, it's a piecewise function, so we have to use limit, the left limit and right limit. It is continuous. That means the left limit equals to the right limit and is defined at that point, right? So we can just use the left limit. What is the left limit? So x approaching to 2 minus. Since it's smaller than 2, we have to plug in this equation. So x plus 3. This is equal to limit x approaching to 2 plus. What is x approaching to 2 plus? Just from the right side, we have to plug in the second equation. So it's kx plus 6. We just plug it in. We can get 2 plus 3, 5 equals to 2k plus 6. So 2k equals to negative 1, k equals to negative 1 divided by 2. We plug it back in, we can get a piecewise function that looks like this. This is x plus 3 if x smaller than 2, and negative 1 over 2, x plus 6 for x larger than 2. Let me just move it aside. The function will kind of look like there's not like a breakpoint. Since it's continuous, this is 2, and they have the same value at like a point that's equals to 5. From the left is increasing like this. From the right is decreasing like this. Let's move on. This is our last topic, and is BC exclusive of our Unit 1 calculus. It's called Intermediate Value Theorem. It might sound very, very daunting, but it really is very, very intuitive. What does that mean? It says if the first rule is f of x is continuous on a closed interval. If you want IVT to be met, these are the three rules that it has to be met, right? So the first one is continuous on a closed interval. The second one is that f of a that cannot equals to f of b, otherwise they'll be the same value, right? So if k is between this value, this must exist a number c between a and for which f of c is equals to k. We can't understand this whole thing just based on words. So let me show you what it looks like on a graph. Let's say this is a, and this is b. And the corresponding value, this is f of b, and let's say f of a over here. If there exists a k over here, let's just draw kind of like a function like this, right? If there exists a k that's in between f of b and f of a, there must be a corresponding value c that's in between a and b. It's very intuitive, right? Let's just try an example. So first of all, we have to see if IVT is met. So first of all, we have to see if the function is continuous. Apparently it is over the closed interval if you draw the graph. So we can say f of x is continuous on the interval 2 over 2 and 1/2, 7. Second one, we have to see if 2 and 1/2 is equal to or not equal to f of 7. If they're not equal, that means our second condition is met. What is f of 2 and 1/2? If you plug the value in, you're gonna get 2. What is f of 7? Apparently is 1 over 5. So they're not equal, so our second condition is met. Number 3, we have to see if k is between these two values. If it is, there must be a value of c that's between this interval. Okay, since 1/4, it is larger than 1 over 5, but smaller than 2, which means that it is between 1 over 5 and 2. Therefore, there must be a value of c that's in between this, and f of c is equals to 1 over 4, and c is between this interval. And how do we find c? We just simply plug x equals c in, right? We can get 1 over c minus 2 equals to 1 over 4. So c apparently is 6. The sketch over here will be pretty obvious. You have kind of like two endpoints. This is kind of like 2.5 and 7. This is 7. Since k is between these two values, its corresponding value will be also in between 2.5 and 7. That this is the value of c, which is 6. Is 6 between 2.5 and 7? So it's yes. This is how IVT works. Let's try more examples. Feel free to pause the video and do your own yourself. Again, first of all, we have to determine if IVT holds. There are 3 conditions. The first one is continuity. Since it's a smooth function, we can say f of x is continuous over the interval -1 to 2. The second one, we have to see if f -1 is or not equal to f of 2. If you plug it in, f of -1 is what? Is -10, and f of 2 is equals to 16 plus 20 divided by -6 is 30. Since they're not equal, So the second condition of IVT is met. The third condition is that we have to make sure K is between these two values. Is 4 between -10 and 30? The answer is yes. Since 4 is between -10 and 30, we can say IVT is met, and there must exist a C that's equals to 4, and the C is between -1 and 2. We just simply plug it in, right? So we have f of c equals to c squared plus 5c minus 6 equals to 4. Simplify a little more. C squared plus 5c minus 10 equals to 0. How do you solve this? We can use the quadratic formula, and we have to find the value that's in between this interval. So we can only use the plus one, so the larger one. So we can get c is equals to 2 minus 5 plus, sorry, it's plus or minus, we can use minus because that'll be out of the interval, and then delta. Pretty sure this is 25 plus 40, so we can get 65. What that looks like on a graph. So we have -1 over here, and also 2. What is the value of f of -1? It's -10. And value of 2 will be like 30. The function will kind of look like this, I would say. It's pretty ugly, but you could tell. Since 4 is between this value and this value, so there must exist a certain value that will let f of, a value c that will let a function be the value of 4. And we just calculated the value that is this, so it's kind of like between this. Okay, this is c, and c is this one. Excuse me here, I made a tiny mistake. The value here will be, if you plug x equals 2 in, instead of 30, I'm pretty sure it's 8. So this will be 8. However, it doesn't affect the result. 4 is still within this range, so we can still say IVT holds right here. So it's given the function f of c equals to x squared plus 3x minus 1. The first question is, does f of x equals to c somewhere on the interval this, from -1 to 2? We should use the Intermediate Value Theorem. Again, the 3 rules. Since f of x is continuous over the interval from -1 to 2. Second, f of equals to 1, f of 1 is what? It's -3, and f of 2 equals to 9. And f of 1 does not equal to f of 2. So the first 2 conditions are met. What about the third one? Is k equals to 4 between -3 and 9? Yes, it is. So k is between -3 and 9. So we can make a conclusion that there's a specific value of c that's equals to 4. And c is between -1 to 2. Based on these 3 conclusions, that we can say IVT holds. Therefore, there must be a specific value of c that's in between this interval. What about the second one? It says, must f of x stand somewhere on the interval of this is IVT. So we know that IVT we know the function is continuous, and these two are not equal. So we have to see if k equals 10 is or is not between the value of -3 to 9. Well, it is not, because 10 is larger than 9, so it's not between 3 and 9. Therefore, IVT doesn't hold here. Therefore, we don't know if there's a c that's equals to 10 during an interval of -1 to 2. We don't know. IVT doesn't hold here. Let's move on. We have to use the definition of continuity to prove that the function is discontinuous at a given value of a. And we have to sketch the graph. We can keep the sketching of graph as homework. We just have to identify if it's discontinuous. So since f is undefined, so x at x equals to 3, f of 3 is undefined. So we can say the function is not continuous. We have to use the definition of continuity to prove the function is continuous at a given value of a, and as a equals to 0. Again, when you see a piecewise function, you always have to use left limit and right limit. What is the left limit? So it's x approaching to 0 minus. Since it's smaller, we have to use -2x plus 2. This will give us a value of 2. And the right limit, x approaches to 0 plus x squared plus 1. This will give us a value of 1. Since the left limit doesn't equals to the right limit, so it is continuous. Our last example is we have to use definition of continuity to find the value of k that makes a function continuous everywhere. Again, when you see a piecewise function, you always have to use the left limit and right limit. So we can use right limit, the left limit, x approaches to 2 minus. Since it's smaller than this and approaching from the right, so we have ax minus k. This will give us a value of 16 minus k. Our right limit, x approaching to 2 plus, since approaching from the right, we have to use x squared plus kx. This will give us a value of 4 plus 2k. Since the limit exists, so these two has to be equal. So we have 16 minus k equals to 2 plus 2k. We can get k equals to 4. So the value of k will make the function continuous everywhere.